So we're going to end this chapter with what's known as the kinetic molecular theory. The kinetic molecular theory, three basic principles. One, the gas consists of tiny particles in motion. Two, the size of the gas molecules is tiny. And so the gas volume, because gas molecules are so spread out, in other words, the volume of the gas molecules is negligible when we compare it to the size of the container. And then we're third going to make an assumption that all of our collisions are elastic. So there's no attraction or repulsion from these collisions. And these are the behavior for why gases exhibit the type of behavior that they do that we can see. Unlike liquids and solids, we can easily compress gases due to the high degree of separation. But in addition, some of the gas laws we've learned about, their behavior is also explained by this theory. So Boyle's law, for example, which says that volume is proportional to 1 over the pressure. Pressure is related to the collisions that the molecules have with the boundaries, essentially the edge of the container. If the volume goes down, then those collisions happen more often. And if those collisions happen more often, then the pressure goes up. The opposite is also true. If we increase the volume, then those collisions with the boundaries of our container are going to happen less frequently, and the pressure goes down. The next behavior helps to explain both Charles' law and Gay-Lussac's law. Recall that Charles' law is that volume is proportional to temperature, and Gay-Lussac's law says pressure is proportional to temperature. So what happens here is as the temperature increases, the rate of the collisions, the number of the collisions increases, and so does the energy of the collisions. And so as a result, if we're trying to keep pressure constant, then the molecules want to spread out more. Or in other words, the volume will increase. If the volume's constant and we have more collisions, then that increases the pressure. And then we have Avogadro's law, where we said that volume is proportional to number of moles. And just very simply, the more molecules we have, it's either going to cause the pressure to go up or it's going to cause the gas to expand. Now, the final thing we're going to say in this chapter about gas laws, we work with the ideal gas law, and in general, the ideal gas law is a good enough approximation. The reality is, real life is more complicated, and most gases don't strictly follow ideal gas behavior. And so we're not going to do it in this class, but I just like to show you that it exists. There is a sort of expanded version of this equation known as the van der Waals equation. And the van der Waals equation is basically to deal with these deviations from ideal gas behavior. What does this equation look like? Well, the right side actually doesn't change. So nRT on the right side. But we see an effect with our pressure and our volume terms. So instead of just saying volume, this becomes volume minus N times B. And our pressure term expands to pressure plus the number of moles squared times A over the volume squared. And these two new terms, A and B, are constants and they vary for each gas. So again, becomes a much more annoying equation to use, kind of like what we talked about with the original forms of Boyle's law, etc. So again, in most cases, the ideal gas law is good enough and gets us where we need to go. But if there's ever a situation where it's not, this is the equation that you would use.